Okay, class, we are going to start the 8.2b lesson now. And we're first going to start with the idea of central tendency. And basically, we're going to start with these three pictures. Okay, so um, first, I want you to take a look at these three graphs. Notice how the mean is, in the first picture, is not really where the most frequent data point is, right? The mode, again, is the data point that occurs the most frequently. And you could see how the mode is higher than the mean in this case. And that basically means, for example, if we were comparing grade scores on a test, maybe the average for the class was a 75%, but the most frequent score for the class was an 85%, right? It seems kind of weird that the average would not be similar to the mode, right? But that certainly can happen, and it's because we know that data points over here can be pulling the average down, right? So again, regarding grades, if the 85% score was the most frequent score, but the average was a 75% score, what do you think that means, class? Like if there were 10 scores of 85, but the average was still a 75, that means this 10 scores of 85 were not strong enough to pull the average closer to each other, or closer to the mode, right? So that means there are a certain amount of negative, or not negative, but just low values that are pulling the average down. Okay. And this is what we call skewed left. Sometimes we also call this a negative skew. And basically, skewed left just means that extreme values on the left pull the mean down, and basically the best description of the class, the most accurate description of the class would be the median. The median is the most accurate, right? Now, what do you mean by accurate, class, or Mr. Quo? Like, what do you mean? The class average should always be accurate, shouldn't it? Well, that's certainly not the case, class. I hope you realize that if I were ever to give you a class average, an average is just a statistical measure, right? That doesn't mean it's the best measurement. Um, it is probably one of the most reliable statistical measurements, but we also know that there are possibilities of outliers. There are possibilities of extreme values that pull the average up or pull the average down. I always like to give this example, class. If we were in school and we were in the room and we measured uh, our bank accounts, okay, including the students, who would be the extreme measurement? Well, the extreme measurement would be Mr. Quo, the adult, right? I have a job. I actually have more than just allowance, and I would pull the average for the entire class in terms of your bank account amount very, very high. But that wouldn't be accurate, right? So I am considered an outlier because I'm in a room where students literally are seventh grade students and don't even have a job. So they have little to no income, right? Maybe your only form of income is your allowance. But when you compare students to adults, then the adults become outliers, and they can really make your data inaccurate. Okay. So here, this is a very, very clean distribution of data where the mean, the median, and the mode are all exactly lined up. So this is what we call normal distribution. This is where everything is according to plan. right? The data is symmetrical. There's 50% of the data on the left of the median, 50% of the data on the right of the median. And with the same amount of low scores, there are high scores. The same amount of decently low or pretty good low scores, there's also pretty good high scores. There's just an even amount, and that's why the data is symmetrical. Now, just because the data is symmetrical doesn't mean it's necessarily a good thing for the um, overall conclusion of the class. Like, for example, let's say that this was the scores of our students, and what if the mean, the median, and the mode was a 75%? I mean, you could say, wow, the data is very, very symmetrical. But again, ultimately, the data is still bad, right? The value is still low. Mean and median are very accurate here. And by accurate, I just mean you can think of it as reliable. You can trust the average now because the data is symmetrical. There are no outliers that are pulling it forward or backwards. Whereas here, the data is not symmetrical. So that means that there are a certain amount of groups on this side that is pulling the average down. And that must mean that if we're talking about grades, there were students that got an F or lower than an F and like lower than a 50%, and they pulled the average down, but overall the class was doing okay. And then finally, our third version, as you may have realized, is what we call skewed right. Or this is a positive skew. And this is where extreme values on the right side, the right of the mean, extreme values on the right of the median pull the mean forward. And what that really means, class, is let's say let's say this was grades again, and the most frequent number was a 70%. The median for the class was like let's say 80%. The number directly in the middle of the class was 80. Yet, how is the average still higher than both of those? Right? If your most frequent score for the class was a 70%, and the number directly in the middle of the class was an 80%, how in the world would the average still be higher than both of those? Well, the only case is there must be a certain amount of people that got 100%, and they're pulling the average up. They're pulling the average to the point where the average looks good. The average is maybe an 86, right? But you'll see that the data is not distributed evenly, right? And that means basically, class, if the data is not distributed evenly, then all these things can start to create bias because you can't really tell if it's super reliable because the data is so it's not evenly spread. Okay, so ideally we want this data to be spread symmetrically because we want to be able to say the mean is this, the median is this, the mode is this, and all three of these things will be considered decently accurate and reliable. Once you have these two scenarios, you start having to dive deeper into why this is the case, and you have to start looking for outliers or extreme values. That's basically what this is, class. Just remember, statistics is a measurement that is supposed to help us paint the picture of the data. Okay, it's kind of like a synopsis, a plot synopsis of the data. Now, what kind of conclusion that we create is up to us, but the data is right there, and you have to create your own conclusion. And this is where there is some bias sometimes. Okay. So from the graphs above, if there is a normal distribution, the mean, median, and mode are all at the center of the data. Most of the time, they are not all exactly the same. So the best measure of central tendency to represent non-skewed data is the mean, right? The mean is king. We usually rely on the mean or the average the most because most often it does display decently accurately. Okay. From the graphs above, if there is a skewed distribution, the mean, median, and mode are all different, right? You can see how they're all different from this picture, and they're all different here. The best measure of central tendency then to represent data that is skewed is no longer the mean. It's no longer the mean. It is now the median. The number directly in the middle is more reliable than the average if you have extreme values, right? I'll say that in plain English. The number directly in the middle is a better representation of the data, is more reliable than the average if extreme values are present, right? Extreme values are bad for data because all of a sudden it can ruin what your data looks like. I'll do another example of this, class. Let's say all of, we had a group of regular 30 adults, just random adults in a room. And again, we calculated net worth, and everyone had they were pretty close to each other. Let's say it was a millionaires club, and everyone had about $1 million to $2 million of net worth. That's a good amount of money. And they're all in a room. And all of a sudden, class, Bill Gates walks into the room. And everyone's like, whoa, hey, Mr. Gates, what's up, Bill Gates? And you realize if you were to take the average net worth of that group, of the people that had 1 to 2 million, and you throw in a billionaire like Bill Gates, he would completely ruin the average of the group. The average of the group would immediately skyrocket to, I don't know, I mean, he's worth billions. And if these people are only worth 1 to 2 million, the average would probably be around 10 to 20 to 30 million, depending on how much Bill Gates is worth. This is a very, very extreme example, but you realize that Bill Gates is an outlier and he ruins the reliability of your data because he's so much further away from anyone in the group. And that is what we call an outlier. Okay. So when you have extreme values, the average starts to become very, very unreliable. And actually, other instances where the median and even the mode may be a better representation of my group, of my data, right? So I'm going to create another, like a classroom. There's a classroom of 16 people. And again, unfortunately, I'm sorry to keep using money and net worth involved, but I think that's where it makes the most sense, right? Let's say this group had the ones were all millionaires, the twos were all 2 millionaires, and you can see how there's that. And then there were also two more ones, 1 3, and then one with a 20, right? So you can see how this 20 is going to ruin all of the data for these people. This is a 20 millionaire, and everyone else here is a 1 millionaire, 2 millionaire, or maybe even a 3 millionaire. Because of this extreme value class, the mean is no longer reliable. You don't want to calculate the average anymore. Instead, something like the mode is actually the best indicator of your data. Okay. Now, hopefully that made sense. Our next video is going to deal with something very similar, but it's going to be another way to display data, and I'm excited to explain that to you. See you then.